Good evening, and it's my very great pleasure to invite Sankar to give his third Chandrasekhar lecture. But please stay back after the lecture for a few announcements. Yeah.
Thank you, Chris. Thank you all very much for staying until the very end of the conference. I know it's very tiring. Even I would not want to listen to myself 3 times on 3 consecutive days. In fact, I cannot listen to myself even once. And you are all here. I'm grateful for that. So we have covered in this conference many topics: spin qubits, topological quantum computation, Majorana Fermions, and fractional quantum Hall effect. I have talked about those 4 topics at some level in the last 2 lectures, but 2 topics that have been discussed extensively in this meeting so far, graphene and topological insulators, I have not discussed at all, and in this talk I will talk only about those 2 materials. I'm going to actually talk about them together, because the aspects of topological insulators I'm talking about closely related to graphene physics with some significant differences. So this talk actually will contrast graphene and topological insulators from pure DC transport perspective. So some points I want to make, that for the purpose of this talk, both of these materials are 2D linear massless gapless dispersion semiconductors. So the low energy spectrum follows chiral Dirac-Weyl equation. For graphene, the chirality arises from pseudospin. For topological insulators, specifically I'll discuss bismuth solenoid surface conduction. The chirality arises from spin. In one case, pseudospin is locked to momentum. In one case, spin is locked to momentum. But for transport purpose, it doesn't make any difference, because I'm interested for this talk, zero magnetic field transport without any magnetic impurities. And this just follows from the non-interacting band theory. Okay. What will be the main physics that I will include is the physics of disorder, which at this stage is very important in both of these materials. And I'll explain what I mean by that. So I'll include both short-range and long-range disorder. Disorder will be the main theme, except for a couple of slides where I'm going to talk about electron-electron interaction. I'll talk about phonons, what phonons do to both of these materials. Let me just give the story away. As you know, you should know, electron-phonon interaction is very weak in graphene. That's why people got very excited that it could be room temperature transistors and so on and so forth. Basically, graphene mobility, a measure of how fast electrons are moving, pretty much the same. I mean, not quite the same, but pretty much the same at millikelvin temperature and room temperature. To give you an idea, gallium arsenide, the kind of samples Jim Eisenstein was talking about, where typical mobility at low temperature is 30 million, if you go to room temperature, mobility comes down to 1,000 or below 1,000 because of strong electron-phonon scattering. So electron-phonon scattering is very strong in semiconductor, but graphene is very, very weak. In topological insulators, electron-phonon interaction is roughly 25 times stronger than graphene. So it's actually stronger than it is in gallium arsenide. So those who are talking about topological insulators as a possible room temperature, electronic device have to keep in mind that it cannot compete with semiconductors in terms of ordinary electron speed and so on. It has to be some other, like thermomagnetic or magnetoelectric device or something else. Interaction effects are typically weak in both of these materials. I'll explain what I mean by that. This RS, the electron coupling constant, is weak. In topological insulator, is very weak. It's of the order of 1/100. In graphene, it's of the order of 1. But you could still have non-perturbative. So if you do perturbative RG, you don't get much. I'll explain this. But you can have strong coupling effect, particularly on the Dirac point, which I would not have much to say about because you have to use a big computer to talk about that. And I personally think disorder masks all of those things, but we could discuss it. I want to emphasize, because many of you work on topological insulator or graphene, I'm only talking about zero magnetic field physics. So some of the very interesting aspects of topological insulator, where you talk about magnetoelectric effect, because spin is the relevant variable there, is not here. I mean, my view is that we must understand zero field transport very well before we can talk about other more complicated things, and that's what I'll do. And I'm talking about monolayer graphene. I'm not going to talk about bilayer graphene at all, because in 1 hour, 2 materials is enough. And when I say topological insulator, all I mean is 2D surface conduction in a 3D topological insulator. I'll assume that there is no problem with bulk conduction whatsoever, which is of course a wrong assumption. All of the current topological insulators are completely masked. The surface conduction is completely masked by bulk conduction. There are these defects, and there is a huge amount of bulk carriers, as Zahid Hassan was telling us. It's improving, but there is still a lot of bulk conduction. I'm going to assume either bulk conduction has been eliminated completely, because materials have improved to the ideal no bulk conduction stage, or better still, that you're working with thin film, and you have applied an electric field to bend the bands so that the bulk is just depleted. So you are just working with the surface. And in fact, this technique has been very successful. Pablo in MIT, Michael Feurer at Maryland, and also Stanford group have basically almost like pristine surface conduction transport using this thin film depletion technique. I'm not going to talk about the experimental technique. I'm going to assume that experimentalists are telling us that this is surface conduction, and this is surface conduction, and those are the experiments I'm going to compare with. We can discuss this issue. So I don't want any complication of taking some complicated two-component transport and reconvoluting it to get surface conduction. So I'm just talking about surface conduction. In the theory, there is no bulk conduction. We can just add the bulk conduction if you know what it is. So my view at this stage is that graphene and topological insulator surfaces are both simple. By simple, you'd see what I mean by simple. Simple means that I can do the theory myself, even at this stage. There is nothing, but you have to include all the realistic effects correctly. They are both gapless semiconductors, 2D gapless semiconductors, but with weird transport properties. And the weird arises entirely from the fact that it's a Dirac dispersion, so you don't expect it to look like real semiconductor, where it's parabolic dispersion. It's chiral, so you expect some matrix elements effects coming from chirality. And most important is gapless. Normal semiconductors are gapless, so you expect some weirdness coming from that. And one point I'll make is that puddles, these puddles that people have alluded to, arising from charge impurities in the environment. So if you have charge impurities in a material, and if you have high electron density, there is no problem. Charge impurities get screened out, electrons don't see the charge impurities. But if you have, let's say that you have charge impurities, and you just put 5 electrons there, what would the electrons do? They'll just collect near the impurities or go away from the impurities. So if you have very low electron density, and then charge impurities are randomly in the environment, the electrons basically become a bunch of puddles. It's not a homogeneous electron gas at all. Average density has no meaning. Experimentally, you're controlling the average density, but the real system is spatially completely inhomogeneous. And I'll show that this physics plays a very important role at low density, and I personally believe Dirac point is inaccessible right now. I'm going to explain what I mean by that. So Coulomb disorder from charge impurities will be very important. I already told you simple B is equal to 0 model. They're both weakly interacting, so this is just a repeat of what I just said, a bit in a more thorough. And a theme would be that puddles are very, very important, and I'm going to discuss puddles at great length. So this is what one sees in RPES. This is graphene, and you see clear linear dispersion. Here is bismuth selenide. Well, it's not as linear, but close to the Dirac point is linear. The valence band is not as linear. This is what we have. This is direct evidence that we are dealing with 2D Dirac material. Now, you should ask, as I did right in the beginning, well, what is this red blob here? And this blob is here also. This line is a guide to the eye. This line doesn't come out of the experiment. Experiment is things without the line. There is this blob here. Actually, there is a blob here also. Those, I believe, are arising from the puddles, and we're going to discuss this. Okay? So you can see dispersion is linear. Here the dispersion is not so linear. So at the end of the talk, I'm going to show you what happens when you go away from linearity. For topological insulator, it's very, very important, I think. But for the first part of the talk, I'm going to keep linear dispersion for both. So what is the difference between the two? Difference is that the relevant chiral variable pseudospin, here the relevant chiral variable spin. This also, so this has only one degeneracy because it's spinless. There is no spin, and there is no valley in topological insulator. So the degeneracy, ground state degeneracy is just 1. Graphene has a ground state degeneracy of 4. Okay, as Amir was talking about, arising from this valley and spin, and that's the main difference. Andre Geim, who is not only a smart guy, he's kind of a humorous guy, goes around giving talks saying that topological insulator is only at best 1/4 of graphene. Okay. At best. Someday in the future, he's willing to concede that it's 1/4 of graphene. Okay. So So this is some more. I'm sorry that I'm not giving the references who did it. This is just random. I'll not even tell you which one is graphene, which one is topology insulator. But if you were paying attention to me, you know that these are graphene. This is graphene also because valence band is so beautifully linear. And these are topological insulator, you can see. And I'm talking about this blob. This blob that you see is connected with blob. This is also topological insulator. So the point I'm making is there's a lot of similarity in their band structure. So we might, and you will see there's a lot of similarity in their zero field transport. This is actually those puddles that I was telling you about. These are actually STM pictures. This is graphene. And this I know is Ali Yazdani's results for topological insulator. This I think is Brian Leroy's data or Cromie's data. I don't remember who. On graphene. And this is what you're directly seeing. I'm not going to discuss in great details. Think of this as a measure of the surface charge density or surface potential. And you're seeing those puddles at low density. You're seeing really the system is not homogeneous. System breaks up into puddles of electrons and holes. Color scheme is blue is, let's say, electron. Red is hole. Similarly here also, system is breaking up into electrons and holes because these puddles form charge. So things that we are going to include in the theory really happen in the experiment. Now, if you do normal diagrammatic transport theory, you're going to do an average, ensemble averaging. You're going to deal with a single density. This physics is completely thrown out. It's like throwing out the baby with the bathwater. This physics is completely thrown out because close to the Dirac point, actually not very close. The root mean square fluctuation in density is much higher than the average density. That means talking about average density is not very meaningful. I'll show you that. Let me start by talking about electron-electron interaction. Since I'm not going to talk about electron interaction in the bulk of the talk, and I know that theorists at least are much more interested in instabilities, phase transitions, things like that, than simple transport or even non-simple transport. So I have two or three slides on electron-electron interaction effect in monolayer graphene. It's a very dense slide, but I'm actually going to go through it slowly. Slowly by a normal person standard, not by my standard, okay? So first, you can actually calculate the correction to graphene velocity due to electron-electron interaction. Same formula applies to topological insulator also because they are exactly the same. You just have to change the parameter. So you can calculate it, of course, within some approximation. Here I'm showing you how the linear velocity of graphene, remember the velocity is linear, how that changes because of electron-electron interaction in the leading order approximation analytic formula. I'm later on going to show results where we just do the calculation numerically. So what you have is, if you have no interaction, so RS is the coupling constant. Never mind what RS is, the same RS that people talked about. It's the fine structure constant of the Dirac material. Okay, it's the strength of electron interaction. And you see there are two terms here in linear order. Let's just leave this out first. This is a feature of Dirac material. This part is kind of this correction you have in all textbooks. If you look at Mahan, you'll see a formula like that. It arises from the fact that electron-electron interaction is long-ranged, and you have to do infrared regularization. You have to do the expansion in screen Coulomb interaction. Otherwise, you face divergence at every level. If you do Hartree-Fock, you face divergence. And this is very well known. This is exact in RS going to zero limit. It was first done by Gelman and Bruckner in the West, and Migdal and Galitsky in the East. And it was all originally done for 3D electron gas. We all know how to do that. It's a sum of ring diagrams, the most divergent diagrams, and it gives you this RS log RS type behavior. In graphene also it gives you the same thing. So this is infrared divergence coming from the fact that Coulomb interaction diverges as 1 over Q. Okay? Leading order interaction. This term is actually an ultraviolet divergence term. Normally in solid state physics, we never worry about ultraviolet divergence. We do not have ultraviolet divergence because of parabolic dispersion. We have natural band cutoff, ultraviolet divergence never shows up. But graphene is different. Graphene is linear. So graphene is quantum electrodynamics, Dirac equation. So as you go to higher and higher momentum, everything diverges in graphene. So you have to put a cutoff. Now you say, well, that sounds very artificial, putting a cutoff by hand. It's really not putting a cutoff by hand. In graphene, there is a real Brillouin zone, and the band actually bends. It becomes something else at very high energy, couple of electron volts. So there is a real cutoff. If I did the calculation with the real band, it will be cut off. So the best way of doing it is to put a cutoff. This Kc is of the order of 1 over lattice constant because it's happening at Brillouin zone age energy scale. So this ultraviolet cutoff, if you are familiar with graphene theory work done by people who follow QED, they completely leave this term out. They just talk about this term because they are not interested in infrared regularization. They mostly talk about ultraviolet. So, but both are important actually quantitatively. You have to keep both. And actually this formula doesn't do justice to the real thing. You have to do the thing numerically. But this is interesting. This is one difference of graphene with regular 2D materials, that you have to worry about both infrared and ultraviolet divergence. And as you can see, as your density, as you lower density, K goes down as square root of density. So as you are lowering density, this term will become more and more and more important. RS is independent of density in graphene in Dirac material. RS is just a constant, depends only on the background dielectric constant. But here I've given you the expression for RF. RF is just E squared. If it was free space, it will be just E squared H bar C. That's the fine structure constant. Here H bar VF. VF is the graphene velocity, which is 1 over 300 of velocity of light. So normally it will be 300 times the fine structure constant. Fine structure constant 137. So in free space, graphene RS will be 2.2. Okay, 300 divided by 137. Here is divided by kappa, background dielectric constant. So it's of the order of 1. Okay, it's of the order of 1. So it's independent of density. But this thing, of course, depends on density. This thing depends on density as square root of density as density, because it's a log. So when you make density very, very low, you will have a logarithmic divergence in your Fermi velocity arising from this. Okay, you have a logarithmic divergence. Of course, this is, and if you can do a part derivative RG, you get exactly the same result if you do a part derivative RG. Meaning, although this is a many-body calculation and leading order ring diagrams, you can write down the RG equation based on that, and you get exactly the same result when you take that, and you get within this scheme, and you can put all kinds of words on it. You can put a 1 over n in front. That's Damson did a very important paper. You call it a 1 over x. Basic point is that you have to somehow justify, if you're a field theorist, why you're doing a part derivative RG. I don't justify things at all. I just do what I can and then compare with experiments. Because in most cases, what I can do is what others can do. Nothing better can be done. And then if it doesn't work, you go work on some problem. But if you're doing field theory, you have to justify it. The way you justify it is you say, okay, graphene has a small parameter. You see this 4? This 4 is nothing other than 1 over the degeneracy. So if this 4 was infinity or very large, this theory is exact. But 1 over 4 is a small number, so this kind of justifies part derivative RG. So let me not talk about this analytic formula. I have explained to you what the basic thing. We directly numerically did the full calculation, the full ring diagram without making an assumption. Yu and Huang did this. This is some of the result. As you can see, and there are various curves here because there are various possible approximations, on shell, off shell. In the leading order, they all give the same result. But if you go beyond leading order, they give different results. Basic point is that graphene velocity, this is all for graphene. Now, I should mention, all numericals I'm going to show you, if it doesn't say anything, it's for graphene. If it's for TI, I'll have the word TI in various places so that you don't get confused. So you can see there could be a fairly large correction. This is all as function of RS, okay, Fermi velocity. And there could be some large correction, but the correction is about order a factor of 2 or something like that. If you look at the spectral, which one? This is the thing is that these are on-shell approximation, so they may not be quite accurate. Okay, so we can discuss this separately, but let me go to the next plot. Some of these questions will be answered. Okay, the important thing is that in the regime one is, other thing you could remember that nothing above 2.2 is physical, because you cannot have RS larger than 2.2 in graphene. So it will go down, but RS larger than, this is very low density. This plot that you're seeing is very low density, very close to the Dirac point, so the denomination could be very large. So the important thing I want to point out, the spectral function, like Rajdeep was showing you spectral function. These are high density. This is suspended graphene. So we want to see if Amir can see some really interesting thing in suspended graphene where the coupling constant is largest. Okay. So high density, nothing much happens. High density, you see some renormalization, but it's nothing much. But if you go to very low density, what we find that the whole Fermi liquid picture almost collapses, because what happens is that here is your quasi-particle peak, but quasi-particle peak basically collapses. This is not a phase transition. This is just effect of very, very strong interaction. I mean, Steve Garvin is old enough in this community to remember these things. This is basically effect like if you make RS very large, what is going to happen, except it's coming from the ultraviolet effect here, not from the infrared effect. So we predicted this. This part is already experimentally observed. This is what the Rothenberg group did. Nobody has seen this kind of collapse. I think it's definitely there. If one can look at relatively low momentum, let's say K half of KF at relatively low density, 10 to the power 10, which is all accessible, I think spectral function will completely disappear. And it is not even a phase transition, it's just effect of very strong Coulomb interaction, okay? What happens at strong coupling? I mean, somebody's going to ask me this question, so I might as well tell you. This is part-orbitive weak coupling RG. What happens at strong coupling? To do strong coupling, you need lattice QCD people, put it on a huge computer, do it. It has been done, because there are nuclear theories to do lattice QCD. This is a subject they can work on. They have done it. And what they find, there is some controversy on exactly the result is, what they find that is a spontaneous generation of mass. Chiral symmetry is broken, a gap opens up. In all language, a gap opens up in monolayer graphene. The gap is, it's sub-MeV. It's a small gap. That's the claim, but some other people don't find the gap. Whether the gap is there or not depends on what the value of RS is. The subject has to be settled by experiment in the end. Right now, I think this order is too high for somebody to settle this subject, but I'm hoping someday Amir will settle this subject, okay? So some of the things, these are interesting questions, but you have to really push your technology to the end, because all of this physics is happening at the Dirac point, and accessing Dirac point is not easy for reasons I'm going to talk about. So this is Rothenberg's measurement. So he actually directly sees these things, so can calculate the velocity from there. He can change the density, and these are various plots, and you can see the slope is changing slightly. Then he can compare with experiment, and this is the best measurement I know. This is a direct STM measurement, just looking at STM. Joe Strossio's measurement is a PRL from Joe Strossio group that came out just 2 months ago. And it actually verifies that the green line that you see uses our theory. These are the actual experimental results. He's directly measuring velocity by looking at the spectral function with an STM tip, because tunneling spectroscopy, STM directly sees the spectral function. Beautiful, beautiful measurement. You know, Joe Strosio has this instrument where he can do STM at 10 millikelvin at 15 Tesla. So, so you cannot really compete with him. If he has sampled, he can just do it. So what he's finding is that it's going up. He's not a Dirac point. Dirac point will have this logarithmic divergence, but in the paper he claims that this formula is very well verified. You know, he gets this agreement. Now, Gaim had a different paper about a year ago where he does transport. He does Shubnikov-Dihas oscillation, and from Shubnikov-Dihas oscillation, by using a lot of theory and fitting, Dingle temperature, velocity, I don't find it very compelling. He also finds that he measures the velocity, and he says that he's seeing the divergence, this logarithmic divergence. He claims, you have to look up the paper to see and he claims that this formula is verified, he's seeing a factor of 3. Here, as you see, they see only 30%. He claims he's seeing a factor of 3, but for transport. I do not find this very compelling. I don't know, world authorities are sitting here, Amir and Jim. I mean, I told Gaim he's a bit, but I trust this. So I think that there'll be more on this subject. I think the question of electron-electron interaction in graphene is important and interesting to the extent you can access the Dirac point. If you cannot access the Dirac point, it's a few % correction only. Because if your KF is very large, then this term you can basically neglect, and this term is not particularly important. Then RS is not very large ever, so it's a few % correction, okay? So away from the Dirac point, it's a few % correction. Close to Dirac point, you have this interesting physics. The Dirac point is being reconstructed, and to what extent it can be seen. This is the current status of the experiment and theory, okay? There is nothing more right now. Amit.
So in Gaim's experiment,
right.
Just looking at the velocity
right.
at relatively high density is about 1.5.
Yeah.
10 to the 6. And
right.
there, at the same density, it's very close to 1.
Correct. And I definitely trust this. What Gaim does is he says, you have to you have to change the background dielectric function. It's like makes no sense whatsoever. Antonio Castaneda told him that it doesn't make any sense. He says, I don't understand. Let me not make any more comment. Okay, so I don't know what the hell he's doing. Okay, I mean experiment is fine, but he gets a theory curve which fits that, and I don't understand where that's coming from. Is what I'm saying. Experiment is whatever it is. Okay, so. Okay, the rest of the talk will be on transport, but we can come back to the issue of interaction. It's very important, and I'm very interested in it. So here I'm showing you transport data. Both of these sets data are from my colleague Michael Führer, who is no longer my colleague, unfortunately, but very, very smart experimentalist who just left the United States to go to Australia, of all places. He's not Australian. He's from Texas. Yeah. Melbourne, not even Sydney. Sydney I would have forgiven, Melbourne. Can you imagine? People from Australia, I have many friends in Australia. They asked me, why Monash University? I said, you have to ask him. Anyway, so this is his graphene data. This is his bismuth selenide data. This paper just came out. This is a few years ago. And what is being measured here is conductivity as a function of gate voltage. Gate voltage changes density around, and I'm going to explain these things. And then in this experiment, he systematically, in both of these experiments, he systematically managed to change the background charge impurity density. It's a very high vacuum, ultra high vacuum experiment where he puts precisely measured doses of potassium ion, very, very fancy stuff. And so since our theory, I mean, both of these papers are specifically to verify or falsify our theory quantitatively. And so he said, okay, the theory is based on charge impurity density, which is typically unknown. I would know how much charge impurity density I have because I'm putting that in by hand. And the point I want to make here, I'm going to come back to these plots. You can see that these two are similar. Okay, the qualitative are very similar, the transport. And this is why I want to discuss both of them together. Okay, they are very similar. They're both approximately linear at higher density, and they both kind of saturate into a plateau around the Dirac point, and these are features you have to understand. And then they deviate, become sublinear at high density. These are the features you have to understand. This time that you see as various potassium doping time with various impurity density, okay? So why does it saturate near the Dirac point? Why does it glow linearly beyond the Dirac point? Why is it sublinear in graphene far above the Dirac point? These are issues we want to understand. This is basically the same thing now, showing resistivity, so that you know. So this is actually Philip Kim's graphene data. This is Michael Furer's topological insulator data, and Philip Kim's graphene data is very similar to Michael Furer's graphene data that I showed you here. These are different samples, and in fact, I am a co-author on this paper because Philip compared it directly with our theory, and theory experiment agree very well. But I have not shown you the theory yet. The point I'm making that transport properties, DC, B is equal to 0 transport properties in graphene and surface of bismuth selenide seem to be universal qualitatively. They're very similar. So that's my logic, that's my rationale for discussing them together. Okay. So let's start with Boltzmann transport theory. Okay. So, Boltzmann transport theory is very effective on a crude level. As long as quantum effects are not very important, as long as you have good reason to believe that quantum interference effects are not very important, this would give you everything. So, yeah. No, this is the technique. Yeah, this is the technique he developed, and I think, so he depletes. And, I can only, I asked Amit thinks this is an okay technique, Pablo is doing it too. Whether it's, it actually worked in his device, a subtraction or not is for the referees, and we have to debate this thing. Okay. But of all the data I have seen in the literature, his data are the best in terms of pure 2D. So he did not have done any subtraction is the claim. Okay. My postdocs are also co-authoring. I'm not because, because of, this is an issue, but that's the claim, okay? So this is the Boltzmann conductivity. So main thing you need, everything here is known, density of states, Fermi function, but we need the scattering time, okay? So suppose I'm at 0 temperature, and 0 temperature, this is Fermi function, so its derivative is a delta function. So you can immediately write down at 0 temperature, conductivity is going to be given by Fermi velocity square, density of states at Fermi energy, and the scattering time at Fermi energy. Well, so let's see what it gives. Let me just tell you that this factor V, so scattering time you have to calculate now. So how do you calculate scattering time? You just use Fermi's golden rule or Born approximation. That's what I meant by everything very simple. It's a lot of work, but it's very simple conceptually. So this is the formula, Fermi's golden rule. And only difference in standard 2D system is that you have this additional matrix element effect because the system is chiral. Since the system is chiral, there is an overlap factor coming from AB or the correct, in topological insert, the correct chiral factor is the same because they're both Dirac material. And this thing is that, and 1 plus cosine theta divided by 2 comes in. So you don't need to know anything about chirality. You may not even know what chirality means. All you need to put is 1 plus cosine theta divided by 2 here. And there is, of course, another 1 minus cosine theta coming from vortex correction. And that's all. So when people say, and you'll hear this jargon right and left, oh, backward scattering is suppressed. All they are saying is that there is 1 plus cosine theta factor. Okay, it's the backward scattering is suppressed is a fancy way of saying there is a matrix element effect which is 1 plus cosine theta because cosine of pi is -1, so it just goes to 0. So it cannot go and come back. Okay, so that's all one is saying because that's completely incorporated here. But I have literally heard people give talks, or I have seen in publications people say, oh, graphene is immune to disorder. This is complete nonsense, okay? In fact, scattering here much, much more in gallium arsenide because 1 plus cosine theta times 1 minus cosine theta is 1 minus cosine square theta. That is not always 0, okay? That is 0 only when cosine square theta is 1. And actually, there's a lot of scattering here, okay? It's just that you do not have back scattering. Unless you're talking about quantum interference, back scattering is irrelevant, okay? All scattering comes into graphene. All right. So now let's make some simple approximation. Let's first start with white noise disorder, which is theorist's favorite kind of disorder. The interaction with impurity just produce zero range S scattering. So you take the disorder to be constant. If you take the disorder to be constant, then immediately conclude from the formula I had that sigma will be independent of Fermi energy, which means sigma will be independent of density. That is it. So this violently disagrees with experiment. But what is more important is that let's look at what charge impurities give. For charge impurities, the electron impurity interaction disorder is 1 over q, but then there is a factor of 1 over e to the power minus qd if they are separated from the plane. They would not be exactly on the plane. If they're exactly on the plane, d will be 0. So d is some small number. So this is the formula. And then you can immediately show if that is the case, then sigma will be proportional to kf squared. So it's going to be proportional to n. It's going to be proportional to gate voltage. And this is the reason most people believe, also almost everybody, maybe minus 1, believe that, but it's a very important one. People believe that graphene conductivity is linear in density. Okay, so because of this. But I want to make a much more important point than experiment. Unless an experimentalist tells me that he or she has made a sample which has no Coulomb impurity at all, then just from power counting, I would say this is irrelevant all when density goes down. This is relevant because this is independent of density. As I'm going closer and closer to that point, this sigma is large, this resistivity is constant, this resistivity is diverging as 1 over n. That means that it doesn't matter whether your sample is dominated by Coulomb impurities or not. If you have even, in principle, if you have any Coulomb impurity at all, this will always dominate if density goes to 0. And this is a point I have not been able to explain in all clarity to at least one individual, okay? Almost everybody else seems to understand this completely, okay? And so as density goes to 0, I don't care what you have. This must dominate. This is the point, okay? And this is a very simple point. Right, Amir, is a very simple point? You are not that one person. You are important. You are important, but not yet that important. All right, so. What? Oh, I can't tell you. No. Okay, so I have made a table here for you where I have done that Boltzmann calculation. This is all in our review article. So you can have various kind of disorder. You can have other disorder also, but these are the four most important one. Let me leave that one out. Coulomb. So the conductivity goes linear in n. Mean free path goes as kf, square root of n. So it always dominates as density goes to 0. It always will dominate. You can forget about everything. Everything else is irrelevant. This is relevant. White noise. Mean free path goes as 1 over square root of n. Mean free path increases as density decreases. Conductivity is constant. It's irrelevant. It gives ballistic as you go to low density. Ripples. You can take ripples. Ripples actually is even higher power. Then the conductivity even, is even larger. So it's even more irrelevant than this. Some people like this resonance scattering, which I'm not going to discuss what it is. It's you have resonant impurities with some structure inside. Then you can calculate what their cross section would be. Impurity structure. There is no spectroscopic evidence they exist, but one cannot rule out that they exist. So if you have resonance scattering, then sigma goes as n log n. Again, this is strong, but this is less relevant than this. So as density goes down, this again will dominate because n log n is a subleading term to n. So yeah.
No, in that first term,
right.
Coulomb going and sigma going
right.
Density.
Right.
It still requires a large number of impurities.
No.
To make it diffusive.
No. So what? Yeah. That's a question of what the sample size is. That question cannot be discussed, from without.
My question is that whether there is a crossover that say when you go to suspended graphene.
Yes.
To graphene on silicon oxide.
From diffusive to ballistic? Oh, absolutely there is. Okay. As you increase, absolutely. I'm going to discuss that a little bit. I'm going to stay away from ballistic thing because it depends so much on, except when I talk about suspended graphene, I'm going to show you some results. I personally believe pure ballistic transport has not been seen because nobody has been able to show me transport where the conductivity varies as a function of length. Okay, unless you show me that, everything else that I have seen, is based on some theoretical fit. Or it doesn't quite look like n. And I'm going to show you results. Completely diffuse, it doesn't quite look like n. And I have discussed it with Philip, and Philip completely agrees with me that the PRL that he published saying ballistic could be the effect we are talking about. Problem with ballistic has a meaning. Conductivity is ill-defined. You can only talk about conductance. So you have to show me conductivity varies the function of system size. As far as I know, nobody has seen that yet. Okay? And the claim always is, oh, these samples are just a few lengths. So that's the experimentalist problem. If you're going to claim ballistic, show me that it changes the function of L is mine. I'm not saying it doesn't happen ballistic, but I think this issue is not conclusive. Okay? So why is the nature of disorder so important in graphene? In metals, it's not important. As you know, you can look at any metal transport calculation. Nobody ever calculates Coulomb impurity. You always assume white noise, and it gives you very good result. 2D, you assume white noise, very good result. All the diagrammatic theory always assumes white noise. Why is it in graphene I'm saying it's going to fail qualitatively? Let me just explain this to you quickly. Experts already know that. So basically, you have to use screened potential. So let's say a Coulomb interaction in ordinary two-dimensional electron gas, the kind of system Jim Eisenstein was talking about. There, what happens is the screening, of course, is proportional to density of state. Right? Screening is basically long wavelength screening is density of states. But density of states in two dimension is a constant. So if the density of state is constant, what's going to happen is this screen disorder is going to go for large density of state just as 1 over disorder. So Coulomb scatterer will look like white noise. They look like they're constant because of this. Okay, so that's why in 2D you don't need to worry about it. You can just assume it to be white noise, it's fine. You're making just some quantitative approximation, not a qualitative approximation, okay? But in graphene, density of state is linear in KF, right? That's a Dirac material. Density of state goes as KF. Because it goes as KF, disorder for Coulomb goes as 1 over KF. It's never constant. So this is the qualitative difference. This is why you cannot assume it to be white noise. And all white noise, so in graphene, everything I'm saying graphene is valid for topological insulator, remember that, okay? So this is just that thing actually calculated explicitly. This is all in our PR11 review article. Let me just skip that. I already made the point, okay? This is again, that point made with the actual equations, but I think unless you have a question, I'm just going to skip this. This difference arises from the linear dispersion, which leads to the fact that screening Thomas Fermi potential in Thomas Fermi wave vector in graphene is proportional to KF. That means screening is always weak in some sense, okay? So this basic theory has been verified experimentally by a number of groups. Here is data from Manchester. Here is Philip Kim's work, which was done, we were co-authors on it. This is very early. Very early in the game, Horst wanted to do a very careful measurement to see if what we are saying is correct, and it turns out that he agreed that it is, and we wrote a paper. This is a very thorough verification of the theory that I just told you, that Coulomb scatterers. Now, what about Dirac point? That's what we're really interested in. So, what? Oh, I should make a point that I have not, because I will not make a point. Somebody should ask me, it's linear here, but eventually it's always sublinear. You see that it's always going below. All of them going below. Why? It should be linear forever if it's charge impurities. That's very simple. In fact, this plot tells you exactly what I was saying. I should have made that point then, but without the figure. Here. Now let's ask, what is important if n goes to infinity? When gate voltage is very large, you're going to n going to infinity. When n goes to infinity, this is least relevant, and this is most relevant. So what will happen is that you conclude that for low n, conductivity will go as linear in n. For large n, conductivity will become a constant. So it will go from a linear to constant. So it will look like it's sublinear. That's all that is happening. Okay. So you have so at large n, whatever point defects you have dominate. At small n, intermediate n, Coulomb scatterers dominate. So at large n, you will always have this Wendover, and that's the reason it looks a little bit like square root of n. Okay. In some situations, so he took Phillips those suspended graphene and showed that this picture fits it perfectly. Okay. With very reasonable parameters. Not unreasonable parameters.
Large n, there was the ripples, which should eventually
come in also, and should bring the thing down, just as in silicon MOSFET. There is a reason I say these things are just like semiconductor. In silicon MOSFET, things come down also, absolutely. Okay, but the interesting question is what happens at Dirac point. So I would say finite density transport in graphene, and I'll show in topological insulator also, more or less understood. I would say almost quantitatively in most cases, subtly qualitatively in all cases, okay? But what about Dirac point? The argument that I gave you, now Dirac point density is 0, right? That's the definition of Dirac point. Dirac point has 0 density. Now if you just take the standard Drude theory and do not think much, then you say, density 0 means conductivity 0. Okay, density 0 means conductivity 0. Sounds good. That's what our Coulomb disorder also gives. Density of state is going to 0, conductivity will go to 0, because sigma is just a product of DFT. But one has to be careful. tau also depends on density of states. And in most models, tau actually goes as 1 over density of states. So you could conclude, no, conductivity will become constant there. I don't want to get into the details, but in 2006, 2007, there are 6 phases of letters by 6 very eminent theorists. I'm not going to show you the slide. It's all water on the bridge. All of which are correct. And each paper concluded the Dirac point conductivity of graphene will be a different number. And the numbers varied from 0 to infinity. I'm not being facetious. It's true. That conductivity could be 0. Conductivity could be infinity. And conductivity could be any value in between. And the value that most liked was 4 square over pi h, which is the value you get if you assume graphene to have no disorder at all and just take the quantum theory of transport, and then you just look at, because you know which university class it belongs to, and you find that it will be 4 square over pi h, and you can do a Landau-Boutique numerical calculation, you get this 4 square over pi h. Okay? So this is, most people believe it's 4 square pi h. In fact, the way I got into graphene was, Philip Kim was giving a talk at Maryland, 2007, beginning of 2007, and he was showing this minimum conductivity, and he was saying, well, he doesn't say universal value, he suddenly doesn't say 4 square over pi h, and I had no idea what he was saying because I did not know anything about graphene. And so I asked him, he said, well, it's supposed to be 4 square pi h. I said, how can it be 4 square pi h? It should be a totally non-universal number, depending on the amount of puddles you have. And he said, what puddles? I said, well, you have charge impurities and so on. That's all, but I realized that this is a problem I know how to solve more or less right away. Let me tell you experimentally what people find. Experimentally, people find conductivity, I'm going to show you the results. Conductivity is sample-dependent constant, very weakly sample-dependent constant, logarithmically, around the Dirac point, the so-called graphene minimum conductivity, okay? And same thing is found for Ti. And you may have already noticed it. Let me see, I should have, yeah. So this is Grimes' original data in the first paper. Here conductivity is coming down beautifully linearly, and then there it becomes some constant. If you expand it, it's not constant, but it's a plateau at a value which, if you look at it, is roughly 40 squared over h. So Andre Geim is a very humorous person, often used to go around giving talks in those days saying the story of missing pi. That's what he called it, okay? And here is data from Michael Feuerer showing some minimum, but the minimum is not always obvious, and this is the band structure effect I'll show you. I'll talk about it. We have to understand why the conductivity as you go to 0 density is not vanishing, as our simple Boltzmann theory says it should, as linear in n, why it's not becoming infinity, as you'd conclude from some theories, or why not 4 square of pi h.
Just get done telling us, though, that if there's no disorder, we're talking about a conductance.
Actually, there the conductance and conductivity are the same.
So did they measure it?
No, they measured this conductivity. So, conductance has been measured by 2 groups.
How did they define the kind of
It's just, what,
geometry?
right. It's a very good question. They did not do any of those things in those days. But then the subject disappeared because of our work, So Jeannie Lau is the only person who tried to make strips and tried to calculate, tried to measure conductance. And it's a paper that you should read and conclude yourself, okay? I mean, I don't want to make any comment on that paper. You probably know that paper, right? So what the physics is, the physics that experimentally was first identified by Amir Yacobi here, is that graphene, those of us who worked in gallium arsenide, we know that when you go to low density, the system doesn't screen. Screening fails. When screening fails, you have these charge impurities. Linear screening fails. You have nonlinear screening, which is very ineffective, and you get these puddles, electron-hole puddles. Here it is in graphene from Amir's famous work. Here it is in topological insulator, somebody else's work. I think this is an STM study. And these puddles have to be included in the theory. But beyond the Dirac point, this is very important because if density is 0, it's all puddles. Basically, spatially, density is some randomly varying number n of r. It's never 0. Only the average is 0. Okay? So average density has no meaning. You have to really calculate the density, conductivity in this percolation landscape, which is not an easy thing to do. So what are these puddles? Very simple thing. If you had just pristine Dirac, nothing, then this is the picture. Okay? You just have Fermi level right at the Dirac point, electrons above, conduction band above, holes below. But if you have charge impurities, then what would happen? The Fermi level will randomly move around. Somehow it will be in the conduction band, somehow it will be in the valence band, and so there will be puddles. In some space it will be here. So spatially, Fermi level will be at different places compared with the bottom or the top of the valence band. Somewhere you have electrons, somewhere you have holes. If you integrate the whole thing over the sample, you're going to get 0 density. But locally, it will be either electrons or holes. It will not be 0 density. You have to have no impurities for this to be 0 density everywhere. So that, yeah.
Is the local Fermi energy
Yes.
higher than temperature scale?
Well, those are details I'm going to come to, of course. You have to include those things, okay? So that depends on what the density is puddle and so on. So there will be temperature dependence induced by this puddle, and I'm going to discuss that, okay? So how do you do this calculation? You can do a simple self-consistent calculation, which we did and published in this journal, PNS, and you can just do a very simple self-consistent calculation. You can say, okay, charge impurities induce some carriers because of Gauss's law, just capacitor, and those they create some potential fluctuation, and you have to do this calculation self-consistently so that you can get the whole thing together, and you can, that's the first thing we did. Now, I knew the real calculation has to be a density functional calculation, which is very hard to do. The real calculation has to be that you use this theorem that Hohenberg and Kohn proved, that the ground state is a unique functional of the density. So you write that down, and you put the disorder in, and solve the whole problem self-consistently. And amazingly, Enrico Rossi, when he came to Maryland as a postdoc, after hearing about this thing, he said he wants to do it. I said, it's not doable. I said, it cannot be done numerically. It's just going to be very hard. He said, no, he wants to do it. I said, no, it's going to take 2 years, which to me is undoable. He said, I'll work on it for 2 years. And he finished in a year and a half, and he found that indeed there are puddles. This is an explicit electronic structure calculation in the presence of disorder, okay? Explicit electronic structure calculation. And basically what you're doing is that, okay, this is the Hohenberg-Kohn functional. If you take the functional derivative of that, you get an integral differential equation which has the graphene kinetic energy, the Hartree energy, exchange correlation correction, and the disorder minus chemical potential. You have to solve this self-consistently, and we included exchange correction. Exchange corrections are not very important, okay? There are some certain conditions you need for its validity, but let me not get into those details. And this is the kind of result Enrico got at the Dirac point. You have electron-hole puddle, and what you find is that this is the distribution of what so there is a peak at 0, but there is a tail, okay? There is a tail. And with exchange, the effect is suppressed a little bit. That's exactly what you expect. Electron-electron interaction tries to homogenize, so this thing is suppressed a little bit. What happens when you go away from Dirac point? Well, let me just show you that it actually does look like experiment. If you take this little piece and blow it up, it looks just like what experiments look at. I'm not going to go into the details. We have done a lot of work on this thing, and it's more or less established that this is capturing, at least semi-quantitatively, the physics of puddles. I mean, it should. We are solving the density functional problem. So what happens away from the Dirac point? This is a busy plot. I'm just going to this direction is density. This direction is just look at one plot. That's a standard plot. This one plot is a standard plot of conductivity as a function of gate voltage, okay? Okay. Resistivity, resistivity, okay? And the different plots, I believe, are basically how much puddles have been suppressed, okay? So this is NC is the density in that gate that he's using. So let's just look at the top one where he claimed the puddles have been totally suppressed, okay? So resistivity shoots up to very high values, over 100 kilo ohm. Okay, over 100 kilo ohm. So he wrote a paper which he claimed he has seen Anderson localization graphene, which is nominally not allowed, as you know, unless you have intervalley scattering or something, because graphene is anti-localization. Okay, so when I saw this plot, I immediately knew that what cannot be ruled out is the phenomena we call disorder by order. This is the phenomenon that I just told you. If you eliminate all puddles, what does Boltzmann theory give you? I just told you what it gives you. It tells you conductivity will go on, resistivity will go on increasing as 1 over n, and resistivity will also go on increasing as t square. And that's exactly what you're seeing. He says, oh, it's Anderson localization, but it's not exponential in temperature, it's t square. And the resistivity changes as 1 over n. So we produce results. These are our theoretical results, and this is his experimental results. These are our theoretical results, this is the experimental results as a function of temperature. So, I would say that, our theoretical results, we can get exact agreement, exact numbers are not known, that's not so important, but our theoretical results look exactly like what he sees. So it's a very strange metal, because how can you have a metal where your resistivity is such that the KFL is much, much less than 1. KFL here is 0.1 or 0.01. We learned very early that KFL controls quantum interference, and if KFL becomes of order 1, then you have the crossover from weak to strong localization, everything get localized. We learned that very early, quantum interference. How can you do Boltzmann? We can do Boltzmann theory. Boltzmann theory doesn't care about quantum localization, quantum interference. I can do Boltzmann theory wherever I want, in a plasma. But why should it apply here is the question. You see, they look very similar. Let me tell you quantitatively they agree, okay? But why should it agree? Is it just a coincidence? I don't think it's a coincidence. I don't want to get into the details. There is a second condition for quantum interference to apply. It is not enough for KFL to be less than 1. You also need phase breaking length to be larger than the elastic scattering length. You know, if you go into a plasma, then KFL could be 10 to the minus 6, but you would not claim quantum interference because the inelastic scattering length is very short. I believe that's what is going on here. We have calculated the inelastic scattering length. It's marginal. At 20 Kelvin, we find inelastic scattering length is indeed shorter than the mean free path. I think that's what is going on, but some localization effect cannot be ruled out. So it's a very interesting open subject, still very actively studied, but you know, this is what we are getting for our result, that as a function of temperature, you know, we see that it keeps on going up and we can get resistivity going very high, very much like what they see in experiments. So right now I would say that the fact that experimentally says this behavior and our Zuber-Boltzmann theory gives this behavior is prima facie evidence this is maybe what is going on. We also calculate inelastic scattering length, and indeed inelastic scattering length, at least at all these high temperatures. Below 20 Kelvin, I'm not so sure. But his experiment goes down only to 10 Kelvin. He cannot somehow do it at low temperature. There is some problem. No, that's the whole point. In this case, because our theory will give a minimum metallic conductivity. As you can see, here also, at very, very low density, he has not reached the depth. So the minimum metallic conductivity will happen when his gate voltage takes him below the impurity density. That's a very, so our theory will always give a cutoff somewhere. But the question is, you know, where is that cutoff? If the cutoff is at 10 to the power 1, you're not never going to see it. That's the point, theoretically. So experimentally, what our prediction is, his thing will also round off at some very high resistivity. Okay, that's the prediction. If it keeps on going up forever, then our theory cannot explain it. Okay.
What do they see and what do you think in your calculations for weak magnetic field at the Dirac point?
Which magnetic field?
Weak magnetic field.
Yeah, so weak magnetic field, what they see is that in weak magnetic field, some weak magnetic field, it's cut off, and that was his reason to say it must be, you know, it must be localization physics. But the problem is that the same weak magnetic field, because the density is so low, magnetic length becomes a very relevant length scale. And I don't know what's going to happen if you do the puddle transport calculation in that weak magnetic field. Okay? No, it's very hard because, you know, nobody has done this calculation problem in puddle. So I don't know what happens. So this is a good point. He doesn't give any data. He just says weak magnetic field is cut off. That's what he says. But the weak magnetic field that he quotes, I don't remember what it is. Okay? But there, if I just calculate the magnetic length, that length is shorter than any of the length scale I have in the problem. So it's a very strong magnetic field for these calculations, okay? And I surmise that our results will change also, but I cannot tell you that it will agree with experiment, okay? So the last thing I want to talk about, because time is really running out, is electron-phonon interaction, because that's something where topological insulator graphene are very, very different. Topological insulator electron-phonon interaction is roughly 30 times stronger than in graphene. So it's acoustic phonon. The calculation is pretty standard, although it's not always easy to do. And if you do the calculation at high temperature, so this is for topological insulator, high temperature, this is the Fitzgerald letter we wrote no, I guess this is our theory paper. So at high temperature, resistivity is always linear due to electron-phonon interaction because it's an equipartition regime. Phonons are bosons, and you have a phonon gas which is increasing linear into. So high temperature, that's always the case. At low temperature, you enter what is called Bloch-Gunayzan regime, where the fact that phonons are bosons come in, and the phonon occupancy is really reduced, and the power law changes from linear in T to the power 4. This region has been seen experimentally by Michael Ford and others. This region has not been seen yet by anybody, but it should be pretty straightforward to see it, okay? So we have done that. Let me just again, this is once you include phonons and puddles and everything in topological insulators, temperature dependence is very complex. So many of these experimental papers where they fit two components and assume all the temperature dependencies coming from the bulk, I think has to be rethought in the context of, but even the surface conduction, puddles contribute, electron-phonon interaction contributes, splitting contributes. It's extremely complex, the temperature dependence. And I have no time to explain it, but let me just say that Michael Führer did a measurement of this. In fact, we did the theory because Michael came to us and said that his temperature dependency is not understanding. So this is a joint paper theory experiment. This is experiment, and we did the electron-phonon calculation, and it agrees very well. The linear T, you have to include the puddles and everything, and the deformation potential coupling that we get from this is 22 eV, which seems to give very good agreement. And this is, as I said, that much larger than what you get in graphene. Michael Furrer did not access the Bloch-Gunayzan regime, which would be very interesting. Okay, so this now phonon. What happens in graphene? Graphene we did some time ago, and in graphene also it's linear in high temperature, but at low temperature Bloch-Gunayzan regime. Now, one important thing is that where do you access this Bloch-Gunayzan regime? Where the phonons that are scattering are fairly high temperature. That's very easy to achieve. Just go to high density. If you go to high density, this thing could move to very high temperature. This thing could move, as you can see, to something like 50, 100 Kelvin. So Philip Kim, who was actually trying to get very high density for a totally different regime, he was trying to make graphene very high density to access the Van Hove singularity to see superconductivity. He wanted to go to 5 times 10 to the 14 per square centimeter. He did not access that, but then he saw a paper. He decided that he may be able to see Bloch-Gunayzan regime has apparently never been seen in any system. That's at least what I hear. So what he did, he went to very high density. This is his data. And you can see this density is very high, above 10 to the power 13. And then he was seeing Bloch-Gunayzan regime above 100 Kelvin. See, beautiful 10 to the power 4 behavior. And it agreed quantitatively with no fitting parameter without theory. The theory that came before, 2 years before the experiment, this theory. And so clearly Bloch-Gunayzan regime is showing up. And somebody should do this experiment in topological insulator. I'm sure it's going to show up there also at fairly high temperature. And the claim is there's the first unambiguous observation of the Bloch-Gunayzan behavior in any solid. In metals or semiconductor, yeah, that's the claim. In metals, you have to do subtract. That's what the paper says. And I asked Philip, I know that Horst tried to do it in gallium arsenide. You may remember that 1990 paper.
What do you mean by Bloch-Gunayzan behavior? Do you mean only as seen in resistivity?
Yeah, only in resistivity. That's what he's talking about here, yeah.
It's seen in other things.
Oh, absolutely. You have seen it in other things. Sorry. No, this is a very, very...
Horst did see it.
No, he did subtraction. He did not gallium. You can go back.
Subtraction?
Huge subtraction because he was in the noise region. Huge, fluctuation. Here it's seen clearly. That's the whole point. It's in resistivity.
So in parallel, Barbados and Singapore also saw it.
That's correct. He just was a bit late, which is, he did, absolutely, yes. What? Well, there is no reason to care. There is no reason to care. No. I think the only point here is that electron-phonon coupling is weak. It's got to be there, and he has seen it, so everybody's happy. So this is, let me just conclude by telling you the differences between graphene and TI. And I would not. So the first difference is spin versus pseudo-spin. This is what Joel was asking me. That, of course, means once you apply a magnetic field, there will be a very differently magnetic effect, many other effects. Quantum Hall effect will be different. The other is, so that will lead to all these other things. But if you can somehow create strain to control pseudo-spin, maybe you can have magnetostrain, which will refer to magnetoelectric, but that's not so easy to do. Then you have spin value degeneracy 1 versus 4. That makes some quantitative difference. And actually, so in TI, you can see a real half integer quantum Hall effect. Background dielectric constant is very different. That will have quantitative differences. Fine structure constants are very different. That will have quantitative differences. Electron-electron interaction will be different because of this thing, but otherwise they will be the same, I believe. Bulk conduction in bismuth selenide, no true topological insulator yet, but I think this problem is getting reduced every day. And if you apply an electric field and bend bands, things are even better. Electron-phonon coupling is much, much stronger in bismuth selenide, roughly 25 times stronger. If you look at the numbers, you notice that. And there is a band structure difference because in bismuth selenide, bands are very nonlinear. And that has a big difference, which I don't have time to talk to. Those are the next 3 slides. But what happened here? Okay, because I have already gone 5 minutes over time, and I'm going to just skip the last 3 slides, okay? Thank you very much. Adi.
So if the bottom line on what you say about the thing and the Dirac point, that it's all classical?
Yeah, here's the thing. I didn't, go on. Now ask again, please.
Is the bottom line of what you say about graphene at the Dirac point that it's all classical? There's not...
It's, what I'm claiming is that if you do not have quantum interference, and if orders are suppressed, then our Dirac-Boltzmann theory should apply to arbitrary value of resistivity. This is not a paper I can write or publish because it's all implicit in our paper. But Gein published a paper saying that he's seeing Anderson localization, where resistivity is increasing as 1 over n and also as t square, which is exactly what Dirac-Boltzmann theory predicts. So we did the theory exactly for his numbers and he reproduced his data. So the question is, why doesn't quantum interference show up for large LKF? And I gave you some plausible answer. The answer to your question is yes. It's either classical, semi-classical, because scattering is still calculated quantum mechanically, but the theory is Boltzmann theory. Yes.
That's disappointing. It's disappointing.
Very disappointing. But that has been my life, deflating very fancy effects with very simple theory, I mean, I'm not saying that's all. Adi, I don't want to be, I'm on some kind of TV. I made a very narrow statement. There is a claim of seeing Anderson localization. We can reproduce those data. And I would not believe a resistivity above 25 kilo ohm coming from a semi-classical theory unless the inelastic scattering length is shorter than elastic scattering length. We verified that to be true in that regime. That is all I can do, okay?
So Shankar, David Goldhaber-Gordon also has an experiment with a suspended top gate showing resistivities going up to 2 megohms now. 2 megohms, and at much lower temperature.
Correct.
So does that theory still apply there?
He claims in his paper that he is likely seeing this thing. He doesn't believe that he's seeing localization. His thing is a bit more difficult to understand, I have to tell you that. But yeah, it's good. And Gaim told me that he has results now going above 1 megaohm also. Actually, he told me he has results going above 1 gigaohm, but he cannot measure above that. This is what he told me. And so my view is that there may very well be some Anderson localization physics coming in also. So let me comment on that. If you have intervalley scattering, Anderson localization could come in. So I have a follow-up paper, which will take 2 hours to explain, where I ask this question. So let's say Gaim is right. Let's say it is localization, right? Because I'm calculating elastic scattering approximately, let's say that it is all localization, and the fact that our theory reproduces data so well is a cruel joke by God on me, because God wants me to write one more paper for some reason, okay? Exactly what I need, okay? So let's say that's what is going on, okay? God is looking how many papers I'm writing, so let's do a joke on him, okay? Let me make it write another paper. Then the question is, it must have intervalley scattering for graphene to have localization. You know what I'm saying, right? And the intervalley scattering has to have some strength to overcome the anti-localization. So then my question is, that intervalley scattering should affect high-density transport also. You can't have intervalley transport which just gets switched on just to produce Anderson localization. Intervalley scattering then should get high density also. So in a follow-up paper, So in a follow-up paper with Kostia Kechedi, we looked at this question very, very carefully. This paper just came out a month ago. If you're interested, and we calculated all the localization corrections, all the anti-localization corrections in this system. We calculated how much suppression of puddles you expect with this gate. I mean, it's really, Kostia did an amazing work, okay? And the answer is that there is a narrow regime where the intervalley scattering could be strong enough to give Anderson localization instead of anti-localization, and weak enough not to give a large effect at high density, so that our theory applies at high density. So there is a regime where it's possible, but then Kostia finds that the experimentalists should definitely see weak and localization effect at high density. It cannot be, first thing you see is just strong localization, okay? So then you must see weak localization effect high density. His work just clearly shows, and you must see the crossover from weak anti-localization to weak localization at high density, which Gaim doesn't see. I asked him, why didn't you do this experiment? He has 3 theorists on his paper, Falco and others. And I said, if you are seeing localization, you must see weak, he doesn't see that. He said, no, he doesn't see anything. So big question mark on everything, okay? So the story is still, I think it's ongoing. I think that we'll see more on this subject. Okay? Yes, please.
This works. First off, you keep saying that electron phonon coupling is very low, but of course you're only considering acoustic phonons here.
Absolutely.
Optical phonons are massively huge.
I completely agree. For me, it's a very good point. I don't want to mislead anybody. I should have continuously said acoustic phonon. I'm only looking at transport. Optical phonon coupling is very strong, and as you know very well, that leads to various renormalization and electron-phonon interaction. And I have done some work on it, but today I was just talking about transport. I stand corrected. I should have made clear I'm talking only about acoustic phonons. And if you look at all kinds of phonons, electron-phonon coupling could be very strong in graphene, and there are strong experimental evidence, Raman scattering in particular, where those things have been seen. Thank you for pointing this out. I agree.
The second one, if I understood correctly, you said there is no evidence of resonance scatters in graphene.
That's not what I said. I said nobody has directly seen resonance scatterer in spectroscopy.
Okay, but there are papers where people have shown experimental indication.
Transport experiments, not spectroscopic experiments. If there is, I do not know. Please tell me then.
Well, there's a correlation between the Raman and the transport, and if Raman is spectroscopy, depends what you mean by spectroscopy.
No, in Raman, you or somebody sees resonant scattering, resonant impurities directly is what you are saying? Yes. Okay, so then I didn't know that.
There's an analyzer by Gauss.
Yeah, so that I did not know. Okay, that's a bit disconcerting. The same group that's pushing resonance scattering also for, so I didn't know about that. Second thing is a quantitative question now. But the point is that, look, this is a minor point. The theory includes resonance scattering, okay? So the only question, the point is that what dominates Dirac point is independent of this discussion. What dominates Dirac point is just, so even I don't disagree. So I did not know about this paper of Gaim, but I'll look at it.
No other question, please join me. Thank you. So Arindam is going to propose the word of thanks. Very important.
Do you need a computer?
No, I need the podium.
Go ahead. I will fix that later.
Okay. Is there something that belongs to you over there?
Everything that belongs to me.
Oh, okay. That's okay. I'll not touch it.
Why don't you just talk?
Yeah. I'm just done.
Okay.
So, right. Can you hear me? Good. So this is the last bit and a very pleasurable bit. So I'm going to thank several people. It will not take more than 5 minutes, so please bear with me because there are many people who have made this event very enjoyable and very successful. And, this sort of started 6 days ago. We are having a little longer week, so to speak, started on a Sunday. And there has been, many people who sort of, over the last 6 days, lost the sense of a week. Because it started a Sunday, which was a perfect working day. I'm thinking today is Saturday or Sunday, or Friday. So I'm a little confused. But anyway, I would like to thank people on behalf of the organizers, which is Krishnendu and myself. First person to, of course, thank is Professor Das Sarma for agreeing to come. Please give him a hand. It's not just for agreeing to come, but also actually taking a very active initiative to create a meeting with very, very eminent personalities in graphene and the Dirac transport and quantum computation community. So without his support, this wouldn't be impossible. Okay. The second person who is not here, of course, is Professor Spenta Wadia, because of without his financial support, this would have been impossible as well. But I have to sort of emphasize that it's not just about money. Spenta had beautiful ideas as well. You see, when we started sort of discussing about this meeting, it was not the school part. We thought we'll just have the meeting, the Chandrasekhar lectures and the meeting. So Spenta said, you're getting people from all over the world who have, achieved great success, and it would be absolutely brilliant for the students to come and see this and interact with them. So the school part was entirely Spenta's idea, and we believed, and we clearly see that it's correct, that we had fantastic school for first 3 days, and I think the lecture topics, as we mentioned at the end of the school, was so beautifully orienting towards this meeting that it seemed like a very seamless crossover from the school to the meeting purpose. And really, I think I would like to thank Spenta. Please, one hand for him, even though he's not here. And I would also like to thank the school speakers once again for making it, a beautiful background information bank for this meeting. And on that note, since the school speaker, apart from the school speakers, I think we would like to thank all the speakers of this meeting as well for giving beautiful presentations, which you can see at the end of the conference, the attendance. It looks that it's certainly the quality of the talks, the presentations, the way people stuck to their timings, everything had been fantastic. So please give a hand to all the speakers of this. It would be impossible for us to, have this meeting here without the support of Professor H.R. Krishnamurthy, the chairman of the Department of Physics. His he has made all the facilities that's reasonably possible available to us to not only use this auditorium, but also to use the premises for our tea, our lunch and breakfast, dinner. This has been a whole round physics performance, and Professor Krishnamurthy is the kingpin in that. I would like to thank the TIFR folks for, they are the one who started from the public lecture, and even during the organization, they have been organizing the ICTS lectures over the last few years. And Kedar, Shubroto, they are all here. Please give a hand to them, because whenever we needed, we could consult them, and they gave us the right suggestion. The ICTS secretaries, Shobha in particular, sorry. There we are. So Shobha, Asha, they are the one who started working on this whole meeting from the day I started working. So really, it's nearly about a year effort that has gone in. Please, one hand for them. I don't know whether they're. I would like to thank, there are two more sections, that's it. I would like to thank all participants, students, who particularly for those who are coming from outside, and for their enthusiasm and active participation. There have been several questions, many questions from the students in particular, and it has been an enjoyable experience for all of us for you being here. And I really hope to see you again in future ICTS conferences. The last, and certainly by no means the least, are the organizing team. Really, Krishnendu and I were sort of doing little bits and pieces now and then over time. But when it actually came to nitty-gritties of the stuff, or the particularly last 2 weeks of the conference, it's really the people who carried out each and every detail should be thanked with a special mention. I would first like to show you the people who actually carried the mic, all the time. Could you please stand up after every questions? Amog, Terence, and Esha. They're all undergraduate students who are extremely excited about being here. And every time there was a question, they just ran from there, because you can see they see the running. Thank you very much. The volunteers team, which belongs to my group mostly, has been absolutely fantastic. I would like to show you starting from your accommodation, from your registration, your food, your network. Everything has been done by them. Srijit, please stand up, along with your team who's looking after the accommodation of all the... Srijit, who else is there? Funny, thank you. So they are the one who looked after your accommodation. Medini looked after all the registration parts. Is she there? Where is Medini? Oh, she's probably sitting at the outside of the registration desk. In case people come. So all your kids and registration team, anyone here? Vidya, Shemanti, they have been looking after all the participation certificates. All the details have been looked after by them. Your transport, from hotel to here, the buses to banquet, coming back. Sai, is he there? There he is. And the transport team, where's the transport team? There. So they are the one who have been looking after your airport pickups at wee hour in the morning, and they went there and got you here.
So it was a zero resistance transport.
It's a zero resistance transport. Kolol. Where is Kolol? Kolol, Amer, they looked after your network ones. There have been live telecasts going on somewhere there. And all your mics, your everything regarding computers, everything has been looked after by them. Finally, Kaushik looked after the food. Anuma, There is. Okay. So that more or less ends the thanking part of the seminar. Really, it's been a wonderful experience. And I wish all of you who are going away from Bangalore today, tomorrow, a safe journey back home. And I wish to see you here again sometime in the future. Before we completely end, just 2 points. Yes, I'll give the mic to you. Any participation certificates, if you need still, please contact Medini, who will probably be standing outside, as I said. And for outstation participants who would like to have dinner here, if you would like to, then it's arranged at 7 o'clock outside exactly at the usual place. Thank you very much.
I think on behalf of outside participants, happy participants, I would like to thank Arindam, Krishnendu and Krishnamurthy and all others who have made this wonderful event. Physics-wise, it was great. Food-wise, it was great. Thank you very much.